Okay, hello everybody. So today Rick will present us another tutorial of some exciting stuff. So please, Rick.
Yeah, so I just wanted to share with you some results of playing with some models of how to relate age, brain, and cognition. And this started with discussions with Roger Kiewit when he was here many moons ago. And it applies to really trying to find the relationship between any three variables. So I'll switch between calling them A, B, C, and age, brain, and cognition. And it starts with a general linear model and then moves on to structured equation modeling. So it might be a nice introduction to structured equation modeling for those of you who don't already know about it. And along the way, it illustrates concepts like moderation and mediation and measurement invariance, etc. The talk might be a bit disorganized because it's hard going through our markdown code in a live fashion. So in a moment, I'm going to open some windows with the HTML produced by the R markdown code. And there'll be a lot of text on the screen. So please try to avoid reading the text and listen to what I'm saying. But I can provide the HTML and the R markdown that generated it for you to play with yourselves afterwards. So we'll put it somewhere on the website if you want to play around some of the parameters or try different things. But anyway, advance apologies that it might be a bit chaotic. So let's start with this window here. Oops. So this is the HTML produced by the R markdown. Again, please try and avoid reading too much at the moment, and this is what I'm saying. At the moment, it's all cross-sectional in the sense that we're going to deal with one observation per participant on each of the three variables A, B, C. In future, hopefully extended to longitudinal analysis. So interested in change over time, where some of these concepts like mediation become much more powerful. So it is cross-sectional, and we're going to start with assuming you had 10,000 participants. It's a large amount, but enough to get sufficient power here. And we're going to generate so in this case of three variables, A, B, and C, we're generally going to talk about the A variable as being the causal driver, or possibly the independent variable in the context of the GLM. And we're mostly going to be interested in the C variable as the outcome variable of cognition, if you like. So one of the questions will be, how does the relationship between A and C depend on B? So let's generate A first. So all this does is generate A from a normal Gaussian distribution with a standard deviation of 10. Now, in a moment, I'm going to show you the GLM. I assume most people here have a rough understanding of linear models in statistics. But in the GLM, you have usually just one outcome variable on the left-hand side of the equation. And then you have a equal signs or a tilde in linear modeling notation in R. On the right-hand side, you have one or more variables. So you're trying to predict the outcome from a linear combination of one or more variables. That's the standard general linear model. So you might want to predict C from a combination of A and B. Although you can generalize the linear model to have a large number of variables on the left-hand side as well as the right-hand side of the equation. That becomes multivariate linear modeling, of which partial least squares and canonical correlation analysis are special cases. But the fact is you still only have one equal sign or one relationship between a set of variables on the left-hand side and a set of variables on the right-hand side. And when you're dealing with three variables, that's the fundamental limitation of the general linear model, is you've only got one relationship, one equal sign, one tilde. So we'll start with this model, but later on we'll move to structured equation modeling, where you can have more than one relationship between the variables. So let's start with a general linear model. I'm going to bring up this window and keep it on the screen, because we're going to generate data. So this is all simulation. We're going to generate data from one model and then fit another model to the data generated by that model. So we know the ground truth here. This is all simulations. So we can generate some data by assuming that A causes change in B or variation in B, and B causes variation in C. So I'll call this a sequential model, M1. Or it could be that A causes variation in B and C, but B and C are actually independent, other than their shared dependency on A. So that's the independent causes model. And later on, I'll get to reverse causality. So the idea of watershed modeling, where we've swapped the order of A and B here. So these are models that we're going to generate data from and also fit equivalent models. When we come to structure modeling, we'll fit models exactly like this. So let's imagine that we generate data from model M1. So it's quite simply, we've got A already. I defined it earlier as a Gaussian distribution. And we're going to say that B is A plus some independent variance. And then C is equal to B plus some independent variance. Okay, so just putting A, B, and C together in a data frame. This will be the data, df1 means the data generated by model 1. So that's data generated by this model sequential case here. So the first thing we can do is fit a general linear model. We're trying to predict the outcome C from a linear combination of A and B. And if you do that, you will find a highly significant effect of B, but no significant effect of A. Even though we know the data is generated this way, so A does actually cause B and B causes C. But the reason, and this interpretation from statistics is actually correct in the sense that we can't find any unique variance caused by in C that's caused by A beyond that caused by B. Another way of saying this is that B fully mediates the effect of A on C. So this conclusion that there's an effect of B and not A is strictly correct in a statistical sense. There's no unique variance caused by A, but you've got to be careful assuming that actually that means that age is irrelevant. Age is not irrelevant here. Age caused a lot of the variance in B, which itself caused all the variance in C. So just be a bit careful in interpreting these cases where you have, well, in this case, ultimately correlated variables A and B. We can also change the relative spread or standard deviation of the B and C variables. So it's the same A variable, we just change the variance of B and C, refit the same model. Sorry, actually, we're taking a model here where we're asking now, does C depend on B only? And if you fit that model, yes, sure enough, there's a dependency between C and B. But now when we add A as a covariate, so this is the same model we fit earlier, now you'll notice that the effect of B is no longer significant. So just all that I've changed is made the B and C have different standard deviations. And you can see that when we change that, we now get to the situation where we would falsely infer there's no, at least no unique effect of A and B. So this is simply because A and B are extremely highly correlated. And of course, we all know that absence of evidence is not evidence of absence. So just because you don't get significant value, you shouldn't infer that A and B are relevant. But it illustrates a problem that comes up quite a lot in these cases, is that you might want to relate brain to cognition. And you think, oh, okay, well, I want to covary out age. So I'll add age to my model. And suddenly nothing's significant anymore. That doesn't mean there's not a relationship between B and C. We know there's a relationship between B and C because we created the data that way. It's simply, A is so highly correlated that there's no unique effect of A and B anymore, or no unique effect of B anymore when we add A. So that's just an illustration of the danger of covering out something like age, which may be causally important. But when you covariate out and you no longer get effect of B, you may incorrectly infer that there's no relationship between B and C. There is, because it's in the model. We generate the data that way. It's just that the model can't distinguish what's caused by A and what's caused by B. So the danger of covariating out A. So we call this the age of covariate situation. And again, the reason for this is an extremely high correlation between B and A here. And so the general model can't tease out the unique contributions of each. So let's switch now to data generated by model M2, where B and C are not directly related. They just share covariance with A. So now, same as before, but B comes from A and C comes from A. So previously that was B there. In model 1, that's B, but in model 2, it's A. So if you were to try and explain variance in C from B alone, you find a significant effect. In other words, you'd falsely conclude that B is related to C, and it's not here. It's only related by the fact that they share variance with A. And sure enough, when you add A as a covariate now, there is no longer a significant effect of B. And that is now a correct inference. So now a situation where you add A as a confound and the effect disappears is a correct inference, because there is no link between B and C here. So to summarize this first part, adjusting for age or not in the general linear model can lead to a correct conclusion. In this case, you can correctly infer there's no link between B and C because they just share common variance with A. But it can also lead to the same conclusion, even in this model here. You get the same result, even though we know that A is driving B and B is driving C. We know there's a path here, but because these are so highly correlated, we can't separate them out when we add A as a covariate. So the reason for showing you this is to try and illustrate some of the problems with the general linear model when you're dealing with correlated variables and you're dealing with just one relationship. So if you want to truly distinguish M1 from M2, you have to move to structural equation modeling where you can have more than one relationship. Hence, the main part of this demonstration is about structural equation modeling. So we can, in structural equation modeling, which here we're using the SEM command with the Levan package. Levan is one of the popular packages for doing structural equation modeling in R. And what the syntax here is very simple. This is just a statistical model of the same way we generate the data. That C is caused by B, and B is cause the wrong word, but C depends on B and B depends on A. So here we're fitting this statistical model, SEM1, to data generated by this model M1. So just generated all the way back here, generated from this series of linear mixture of Gaussians. So if we're fitting this statistical model to data generated by that conforms to that model, we can do what's called a chi-square test of whether we can reject the model given the data. So here's a different type of inference. This is not significant, meaning that we can't reject the model given the data. In other words, the model seems to be a reasonably good fit to data, as we expect it to be, because it's generated. The model assumes the same structure as generated data. But we could construct another model that B depends on A and C depends on A. So now our statistical model is this one. And we're going to fit it to data generated by M1. So that once again, this is the incorrect statistical model now, SEM2, fit to data generated by model M1. Here, we do reject the model. So if the data comes from M1, but we fit the wrong model M2, the data is enough to reject this. So using structured modeling, we can start to tease apart what the underlying structure is. And in a moment, we'll do the opposite. We'll generate data from M2 and show that a model that conforms to M2 fits better than the model that conforms to M1. So some other stuff in this, some subtleties about model comparison, which you can read about if you really want to get into model comparison. So here we are, this is now data frame 2. So this is data generated by model 2. And we're going to fit two structural equation models, one the incorrect model SEM1, and one the correct model SEM2. And now, rather than trying to reject the data, just to illustrate that the another advantage about structural equation modeling is you compare two different models of the same data. So this is using a simple ANOVA function, we can compare which of these two models is a better fit. And it turns out that model 2 fit to the data generated by that way is a better model fit. In terms of chi-squared, I'll explain degrees of freedom another time if you're interested, but in terms of chi-squared and AIC and BIC are alternative measures of model fit that take into account the complexity of the model, number of parameters. And even though, for reasons I explained, if you want, this one has slightly more parameters, it's a better fit. Lower AIC and lower BIC are better. So model comparison tells us that when the data is generated by M2, you can fit the data better with a model M2, just showing you can recover the true model. So again, something you can do in a general model, you can't do that. You can't separate the relationship between A, B, and C, but with the structured model you can. When you have 3 or more variables, you can have 2 or more relationships. So we've shown that with this ambiguous situation you get with a general model can be resolved by structured equation modeling. We can find out whether the structure of the covariance matrix is better fit by M1 or M2. Basically, what structured modeling is doing is you have 3 variables, so you have a 3 by 3 covariance matrix from the data, and your model produces a predicted covariance matrix, and you're seeing which of those models get a better fit to the actual covariance across these parameters. Another thing you can do is move on to M3. If we generate the data from M1, but we could say, well, what if A and B are reversed in order? This is sometimes called the watershed logic. You compare different orderings of variables. So this doesn't make much sense, perhaps. So if you think about these as brain, age, cognition, it doesn't make much sense that brain could cause age and age cause cognition, but maybe there's a way of doing that. But the important point is that we're going to show that you can infer something a bit closer to directionality, not necessarily causality, but directionality, by comparing this direction between 3 variables and this incorrect direction. So SEM3, we're now saying that C is caused by A and A is caused by B. So we've swapped A and B. And we fit that to the data generated by the first model. In this case, we can't reject the model fit to the data. But if we compare the AIC and BIC, you can, if I remind myself, oh, sorry, this is SEM1, sorry, yes. So we can't reject the true model, that's as expected, but the data can reject the incorrect model, SEM3. And again, if you look at the AIC and BIC across these models, it's actually higher for the incorrect model. So now we've got a situation where the chi-squared gives us a different answer to the AIC, BIC. And that's because of another issue, which is the fact that the AIC and BIC are sensitive to the scaling of the data. So it's a lot, I think this is a digression, but be careful when you're using different metrics. The chi-squared has correctly said rejected this model of data and not rejected this model of the data. But when we compare the AIC and BIC of these 2 models, ironically, it's better for model 3. If you z-score, so in R, the command scale removes the mean and scales by standard deviation. And if you z-score, the AIC and BIC now will favor the correct model. So just be a bit careful with AIC, BIC. They can depend on the scaling of the data. But if you z-score your variables, then that problem no longer arises. And the chi-squared agrees with the AIC, BIC in favoring the true model from the incorrect model. And so you might use that to try and infer a bit closer to directionality, which variables is primary in the model. So again, some extra stuff that you can play with if you want to, and some notes about model comparison, because there are some, you can't compare any model. With the chi-square test, you need to compare nested models. With AIC and BIC, you each have the same variables in the model and the same set of paths. Was there a question on that?
Yeah, I'm just wasn't sure why was the process different here? Why did you not compare the 2 models and instead compare each one to the null, like M1 and M3?
So we have compared. This is the result of comparing model 1 against the null, or at least does the data reject the model? And no, it doesn't. The true model is not rejected by the data here, but it is rejected for model M3. So the chi-squared test confirms what we know is to be true. So the data do not reject the true model, but they do reject the false model.
Yeah, but can you also compare M1 and M3 directly as you've done before?
You can do, and you get the same results as this.
Okay.
So these are independent of whether you're comparing models or
not. Okay.
The chi-squared, yes, you could work with chi-squared for direct comparison. I think it would be significant to be favoring the true model.
Mm.
But I digress to explain why the AIC, BIC do not agree with the chi-squared here. It's because the chi-squared is a likelihood ratio, and it's independent of scaling.
Mhm.
How much additional variance can explain in the data? What proportion of variance is explained by additional degrees of freedom? The AIC and BIC are essentially the scaling of the data. And if you imagine here, if we take a Gaussian, we take it and we add a bit more Gaussian, and a bit more Gaussian, the spread of C is larger than the spread of B, and the spread of B is larger than the spread of A. And the AIC and BIC will depend on absolute bit of data, and will then favor models where there's less variance than the out. If there's a larger range of the data, the AIC and BIC can be worse because you're not fitting that as well. If you z-square everything,
Yeah.
the chi-square and the AIC and BIC agree again. Sorry, so there's some subtlety here in what model metric or what metric you use for model comparison. So beware, and you can read more in the markdown about this. But I guess the point is that we can, if we scale data or if we use the chi-square test, we can recover the true directionality between these variables by comparing this model with an incorrect one. So that's sometimes called the watershed idea. Let me get this right. I want to show the figures at the same time. So just let me move this window to, we're now to consider more variables. So let's look at model 4 first. We'll use this later on to talk about mediation, but for the moment, just to show you that we can also reject overcomplete models. So if we generate data from M1, remember M1 just goes A, B, C. It doesn't have a path between A and C. So we generate the data just going A, B, C, but we fit a model that has an extra path here. In other words, it's overly complex. So we're going to define SEM4 as the same as SEM1, but additional direct path between A and C. So if we fit SEM4 to data generated by a simpler model, model 1, which was on the screen earlier, and compare them, we, in this case, we can't, so this is what Ronnie was suggesting, compare the models directly with chi-squared. We can't reject it using a chi-squared, but you'll notice that the AIC and BIC are, albeit small, are lower for this model, because, so basically, the models can fit the data equally well, but you're using an extra degree of freedom in this model by this path, and the AIC and BIC punish number of parameters. So the AIC and BIC favor the true model because it's more parsimonious. It uses fewer parameters to fit the data just as well. So this is a converse case where the chi-squared isn't very informative, but the AIC and BIC can distinguish the models. Yeah, Alex?
How do you interpret the difference between there's 1 point difference in AIC?
Yeah.
Is that informative or not?
Yeah, other error bars in AIC and BIC. I think you can calculate error bars with permutation testing, but no, here the absolute value is rather meaningless because it depends on the number of participants, the standard deviation of the data, etc. Because it's actually a fit to the thing earlier. The scaling of the data matters. So the absolute amount doesn't matter so much. Here, I think if you could run it multiple times, different seeds, and you actually there's another part of this demo where it does that, and you can show that it's consistently lower, no matter what the random seed is. And the AIC BIC differ in how much penalty is to the number of free parameters. One is proportional to the number of data points as well. So, but generally the lower the better. But if you're not confident, if that's such a small difference, you're not confident, then run it many times with different random seeds if you're, or permute your data in some way. Anyway, so the purpose of that demo is to say that you can also, so the true model is a subset, or it's nested within this model here, and you can use structured modeling to say I don't need this connection direct one between A and C. But another reason for showing this model is it also illustrates another concept called mediation. So mediation is basically saying how much the relationship between A and C is mediated by, or if you like, depends on B. So does the effect of age and cognition, is it because of changes in the brain. So what you do in mediation analysis is you can do mediation analysis in many ways. You can do it with the general linear model. So general model, you'd say, I do a separate set of fits. I say that firstly, there is a relationship between age and cognition. And then I test, is there a relationship between A and B? And finally, I test, is there an effect of B on A, even when including both in the model? So I'd regress C on A, I'd regress B on A, and then I'd regress C on both of them. And if there's a direct path here, so there's effect of B beyond age, and this path is significant, then you say it mediates it. But it's much more elegant to do it within a single model fit in such equation modeling. In such equation modeling, you basically ask, we fit this model of data, are these two paths significant? And when you multiply them together, how much of the variance do they explain? In a standard way, you basically say, does the path between A and C get smaller when you add B or not? That's the standard way of doing it. But in the structured modeling, you can basically ask the same question by looking at the paths. So what we're going to do now is we're going to generate new data that is generated by this model. So B is caused by A, and C is caused by A and B, that way and that way, and some additional independent variance. So we've now got DF4, which is data created by this model. Then we're going to fit SEM4, and this just mimics the same way data were created, but this is just Levan notation for making the parameters of these paths. So B1 is the path between B and C, making them explicit so we can do some additional maths with them. So these parameters always exist, but we're just going to make them explicit in this notation. So these are what we're going to estimate, these three variables here, sorry, these parameters here. And then the total variance, or explained in the model, is this path, which is A1 times B1. We don't care about the sign here, plus this path, whereas the mediation one is just this path times this path. And you can calculate the proportion of mediation, which is how much variance explained going this way compared to the total variance explained. So we fit this true model to the true data, but ultimately we can come out here and we can ask, what proportion of variance in C is mediated by B? And the answer is close to 0.5. And this is highly significant. So you'd say here that B at least partly mediates the effect of age on cognition. There's still a direct path between A and C here. So this is the p-value here. There's still a significant direct path between A and C, as there should be, because we created data that way. And that means that this is not a full mediation. In a full mediation, there'd be no need for this path anymore. So if you fit this same model to data generated by model 1, it should reject, there'd be no need for this path here. In this context where we generated data where there was a contribution of A and B, and it's an equal contribution, and therefore both routes explain the same amount of about half the variance each. So that's a partial mediation. So mediation in cross-sectional data can sometimes be hard to interpret. There's a paper by Raz and Lindenberger here, which criticized any mediation analysis in the context of aging on cross-sectional data. So mediation is much more powerful with longitudinal data, which I'm not going to demonstrate today, but hopefully that's a plan for future to illustrate how cross-sectional data, longitudinal data are much more powerful to make inferences about mediation. Another concept that comes up quite a lot is moderation. That's different from mediation. So in moderation, we're asking, does the effect of B on C depend on A? So it's like an interaction. So it's sometimes depicted this way, where the variable A impacts on the path between B and C. It's easier possibly to think about it this way. There's two ways of testing moderation. I'm going to show you testing it within a structural equation modeling, within a structural equation model, and between structural equation models. They're both valid ways of doing testing moderation. In fact, they're statistically equivalent, which I can also show you if you want. Let's start with a way of doing it within a structural equation model. What you do then is you create a new variable, which is the element-wise product, or the interaction between A and B, and also input that into C. So this is the first case, is moderating within SEM, this case here. So this is just a depiction, and that can be done in these two ways. So now it's important for creating this interaction term AB to mean correct. So we're going to just z-score A and B and create a new variable AB, which is the product of A and B. And we're going to generate some data where there's an effect of B, but also an interaction term. And you'll notice that actually the distribution now of this interaction term, AB, is highly non-Gaussian. That's very typical when you take the product of two Gaussians. The product itself is not Gaussian. Just a general word, in the general linear model, your only assumption is that the residuals come from a Gauss distribution, or the error is Gaussian. It doesn't matter what the distribution of the predictive variables are in the general linear model. It doesn't matter what the distribution of your independent variables is. They could be anything, as long as the residuals are Gaussian. In such equation modeling, the only assumption is that variables which have arrows onto them are Gaussian. In this case, A times B and B can have any distribution. So it doesn't matter for the stats that the distribution of this term AB is not Gaussian, because there's no arrow coming into it. And it's just the nature of the stochastic modeling is that you assume normality only for what are called the endogenous variables. Endogenous variables are ones that have arrows into them, as opposed to exogenous variables, like in this case, these two, which don't have arrows coming into them. There are extensions of Levan and structural modeling in general which can handle non-Gaussian data. You can do it on count data, for example, where you have these different robust fitting mechanisms, which I won't go into now. So this is all using the standard maximum likelihood estimation, which assumes Gauss distribution. So if you do have non-Gaussian endogenous variables, there are steps you can take to fit models, but let's keep it simple for the moment. So, so we generated some data by M5, and now we're going to fit the data with the correct model here. This is the full output, and the basic point here is that the link between A, B, and C, so this path here, is highly significant, as you would expect. And so you could say that the effect of B on C is moderated by A. That's testing just the interaction term within the SEM. This is a linear interaction term because we assume that A is a continuous variable, B a continuous variable, and we're just taking a linear product of the two. We can also test moderation across SEMs by basically creating a simple SEM where B causes C, but splitting the data into two halves. So here I'm going to make age categorical. You're either under 53, which is my age, that makes you young. Notice that the equal sign is very important because I'm still young, or over 53, in which case you're old. So now you take age out of the model and you make it as like a meta variable, and we're going to compare two SEMs. The gist of this is to compare one model, this is called multi-group SEM, but we're going to compare one model where the paths between B and C are equated to be the same across age groups. That's the equated model where this relationship does not depend on age. We're going to compare that to a model where these are free to vary in the two groups. Now, if these are free to vary, it's like saying there's an interaction between age and brain, since the effect of B on C can vary with or depend on the age. So using what we can do here is we'll define a new variable called binary age, which is a 1 or 0, depending whether you're over 53, called young and old. We have a very simple structured model with only B and C in it. But use this new extension, this additional argument in the SEM function, which is this categorical variable that defines groups. So Levan can do multi-group SEM. We're going to fit the free model first. So in this model, which has no constraints in it, so these paths can differ for each group. Yeah, you go down here, you get some results. If you Oh, sorry, I forgot to mention, I'm fitting the data generated by this model here. So DF5 is this continuous interaction, which we'll come back to. So we've got a continuous interaction reality, but we're fitting it by a binary interaction or binary levels of age. But what you can find in this case is that in the old group, there is a significant relationship between B and C, but in the young group, it's not significant. So suggestions that there is an interaction. But to test that formally, what we do is create another model, which we call the equated model, where, I mentioned that these are the explicit, making the parameters of the model explicit. This is Levan notation by saying, take this path B1 here and make it the same in both groups. If we had 3 groups, we'd have B1, 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 but basically this is forcing the model to equate these paths in both groups. We fit that, and this is the key command. We then compare these 2 models, one in which that path is free and one in which is equated. And if we get evidence supporting the free model, that's evidence for a moderation effect. And sure enough, the free model has lower AIC, BIC, and is significantly favored in the chi-squared test. So even if it has more degrees of freedom, it's still a better fit to the data. So that's how you would test. That's how you could test moderation another way, by taking age out of the subsequent modeling and making it as a grouping variable. Now you might be wondering that this is a linear and this is a categorical interaction. Well, you can try it with the code. If you make age a binary variable and then repeat this model, you actually get exactly the same statistical value, exactly the same Z value or Z statistic for the interactions you do in here. So these are statistically equivalent. When you make age binary in both of them, they are statistically equivalent, which is reassuring. They're doing the same thing basically. But of course, this is more flexible. You could have 3 groups, 4 groups. You could possibly have non-linear effects, which you could do here as well, but it gets a bit more complicated. Whereas this is a better model. So bottom line is, if one of your factors is continuous, then it's better. This model is better, and you can make it non-linear by having a quadratic effect as well. Whereas if your variable is quadratic, this model is potentially more flexible if you have more than 2 groups. But if you make a categorical, you get exactly the same statistic as this bit here argues with these 2 approaches. I've nearly finished, but I want to introduce latent variables, which is the real power such equation modeling. So let's move down to this figure on the right. So this is the real power of such equation modeling, is to distinguish 2 types of variables. So let's imagine that the square box means a measured variable, and the circle means a latent variable. So we might have 3 different measures of cognition. We might have 3 different cognitive tests. I don't know, could tell, spot the word, some other test, etc. But the point is, we're assuming that there's one underlying cognitive ability that underlies those 3 tests, and we want to estimate that from the data. And this model allows the fact that different tests may have different sensitivities. You have different residual error on these tests, but together you extract, if you like, possibly a more sensitive measure of cognition. If there's only one true underlying cognitive dimension, this will be a more powerful model because it takes the information from all 3 tests, allowing them to have different variances. So it's like almost like doing a PCA, if you like, of the measures, but better than a PCA. So the model will estimate a new set of values for each participant for this latent variable C. Likewise, we may have 3 different measures of the brain. We might have white matter, grey matter, ventricle size, whatever. And if we assume there's a single underlying common brain health variable, then we can estimate it this way. So in Levan, we're also going to add age now as a categorical moderator of this relationship. So we're going to estimate latent variables of brain and cognition and ask, does relationship brain cognition depend on age? So what we do is there's a sorry, this is just defining that. This is defining the data. Sorry. So we're going to do the same thing we did before. Age is now a categorical variable. We'll create the interaction term, and then we're going to create simulate measurements C1, C2, C3, which come from a true underlying cognitivity for each person, plus independent noise, measurement noise here, the standard deviation of 1. So we can see these are quite precise measurements. So this just generates the data. So this have a new data frame DF6. So we only have these 6 measured variables and our binary age variable. Those are the data, and the model, we're going to infer the latent values B and C. So I can actually now simulate a final concept, which is measurement invariance. So we're going to compare, again, a free and equated model. In the free model, this is how you denote in the van that this path here is a relationship between a latent and a measured variable with the equals tilde, as opposed from the tilde, which is just a regression. The tilde here just means a regression, so this is simple regression, but this is a special type of regression where you allow independent noise for these components. So you distinguish the measurement model, which is this part here that relates cognition to its measurements, from the structural model, which relates the underlying latent variables. This is kind of this is the historical relevance of structural cognition modeling. You have a structural and a measurement model normally. The measurement model is a bit like confirmatory or exploratory factor analysis, by the way, same concept. So we're going to compare two models, and in the free model, if we have two groups of people, young and old, we're going to ask, are these paths here, the measurement paths, do they differ with age, or are they the same for age? In other words, can we measure cognition the same way in young and old people? Or do our three tests capture the same thing in young and old people? In this case, they do, because we created the data where they come from the same underlying cognitive variable for each subject, which is independent of age. So in reality, these paths are age invariant between C and C1, C and C2 are independent of age. But can we test that? Because if our measurement tool did vary with age, it'd be important to know, because we want to have the model that can capture that, and therefore test whether any direct relationship between B and C is on top of the fact that the measurement itself is changing with age. So it's a good thing to test generally, this idea of measurement invariance. And we're using the multi-group SEM to do that. So this is the free model, just specified as here. And this is the equated model where, again, we're forcing these paths here. We're not affecting this path, just the paths that relate the latent variable to the measurements. We're forcing these to be the same across young and old. So now we're equating just the measurement pathways. And again, in reality, these do not change with age. That's how we generate the data. So we expect, in this case, the equated model to do better than the free model, because it's a better explanation of the data. So again, two models, all that differs is that we're constraining the parameters in one model to be the same across age groups. Name those paths that relate the latent variables to the measurements. So we fit both models, then we do the ANOVA. We're fitting the same data, DF6, and we're comparing the equated to the free model. Here, there's no difference in the chi-squared test, but the AIC-BIC is lower for the equated model. So even though it's a more complex model, sorry, it's the other way around, sorry. It's a simpler model, there's fewer parameters. So I'm sorry, there are few, this is degrees freedom in the data. So there are more degrees freedom leftover data because there's fewer parameters in the model. But anyway, that's why the AIC and BIC are lower, is there are fewer parameters here and explain data just as well. So AIC, BIC support measurement invariance. In other words, the equated model is a better model, more parsimonious model than the free model. And that's what we expect because the data, these paths did not vary with age. So we're using the same tool of this idea of moderation, using multi-group SEM to test something called structural measurement invariance. And this particular example, that measurement invariance is true, but it might not be in other data sets. So it's a good thing to test. So that's actually it. You can see here that I'm hoping to extend this sort of argument, if it's useful to people, to longitudinal data, where you can also talk about mediation and moderation in longitudinal cases. I know there's a lot of expertise here in the CView, particularly in Amy Auburn's group on longitudinal modeling. I'm still learning because it's a very complex area, but I hope to understand it by doing simple simulations. So again, I'll make this R Markdown code available to you. If you're new to structural modeling, I hope it will help you. I find it quite intuitive to learn from simulations and coding rather than from a textbook. But in future, maybe I can come back if people want in 6 months and extend this to longitudinal data. But I need to learn a lot first. But yeah, happy to take any questions. Apologies if there was boring or relevant, but maybe some of you got something out of it.
I will first ask the audience here, are there any questions? So there is something on the chat.
You want to stop recording? I don't know if you want my questions recorded or not. Don't mind.
I don't know. Give me the questions. Does anybody mind recording questions?
Okay, thank you.
I'll start with a rather naive question, but at the very start of your talk, you were talking about the sequential causes, the sequential model,
Yep.
and you showed that with a very high correlation between A and B, neither A nor B came out as significant.
Yes.
I was trying to understand that for a more intuitive point of view. The idea is that since they both show the variability that's within the data, both A and B explain are used to explain part of it, or could you?
So there's something here that I am using. There's different variances of the linear model. What sum of squares you might go to type 1, type 2, type 3 sum of squares, but this model I'm doing, the easy way to think about it is an effect is significant if it explains unique variance. So the test we're doing here is, does B explain unique variance beyond A? And conversely, does A explain unique variance beyond B? So we're using what's called simultaneous sum of squares. So in this linear model, an effect is significant if it explains unique variance. And when A and B are so highly correlated, basically it can't, there's no unique variance for each. And so high correlated that there's a common variance. So the model fit of both A and B is very good. So if you ask the overall model fit, the GNN is fitting the data well, but it can't tease apart when there's unique components of A and B, which is potentially correct in the sense that there should be unique effects of B, but they're caused by A and B as well. So it's a rather contrived example. But the reason I had this high correlation between A and B was just to illustrate how sometimes if you add age to covariate, effects can disappear, or they can not disappear, and it's hard to interpret what happens when an effect disappears when you add a covariate, because the compound covariate can be very high correlated, and it doesn't mean that just it disappears. It actually there wasn't any true effect of B. So let me say another way. We know that B causes A, and if you regress just B and C, highly significant. If you add a confound A, that can disappear. It doesn't mean there's actually no true effect. It just means it can't distinguish the unique variance of each.
Thank you.
And I also use this example to argue that in this case, if you add A as covariate, you do get the right answer, because if you only regress B and C, you get a significant effect. That's only because they share correlation with A. Once you add A to the model, that effect disappears, and that's a correct inference now. Effect becomes non-significant with a compound because in this case, A is a compound. In this case, it's not. So it just illustrates the limitations of doing a general linear model. It's hard to distinguish these two models with just a general linear model and adding a covariate on.
Thanks, Rick. Excuse me, some minor clarifications on the very last example that you gave. I was just trying to figure out what the notation was for the equated model. So if you just scroll down a bit more. So each parameter has two C1s and C, so lower down, here, where you're doing the measurement model.
Yeah.
Why do they have two parameters?
Yes, the reason they have two is there's two groups.
Oh,
so it's just the way that the Van notation. So these are exactly the same models. So they're the same everywhere except that here, the parameter that relates C, the factor C, latent variable C, to the first method C, that can be different in both groups. Whereas this is an explicit way of making them same. I think if I change this to C2, I change that to C3 and C4, and this to C5 and C6, in other words, different variables, it'd be equivalent to this model here. So it's just a notation effect. It's saying, if I had three groups, it'd be C1, common C1, common C1 to fix them across groups. So it's just the way that Van does things. But this concept of comparing models where one set of paths are fixed and one where they're free is a very common concept for structured modeling. So it's quite often done. You can also actually compare a model to another case where you zero a path, which is the thing you should do if you want to use chi-squared to test models, whether a path is significant or not.
Thanks so much, Rick. I haven't tried to use structural equation modeling at all, so this is really illuminating. Thank you. So obviously I don't use age usually, but we do have situations with correlated predictors. But I'm trying to think through, what do you do in a situation where you're not sure you want to make a statement about A causes B? So in our example, when we look at brain lesions and how they relate to cognition, we always have the finding that the total lesion volume predicts everything, and total lesion volume is correlated with, say, the extent to which a lesion affects a particular region you care about, like the MD system. But would you want to say that the total lesion volume causes the volume within a particular network? Like, possibly not. I mean, is it just a situation where we couldn't use this, or because it's sort of obviously attractive to try and think about what is the pathway direct, or is it mediated by these different networks?
In that situation, you should use structural modeling to try and distinguish different possible causes for your data. Maybe I shouldn't use the word cause, really. Nothing. SEM can't really tell you about causality, but sort of directionality of connection. So, bottom line, when you're in a situation where you've got two correlated variables, you don't know which have unique effects on the outcome variable. So in your case, you're trying to predict cognition from a local lesion volume and total volume, lesion volume, whatever. Those two are correlated. If you find an effect of the local lesion volume, regardless of whether you add total as a covariate, then that's the best outcome. You're happy then. The ambiguous outcome is when an effect exists without a covariate, or when the other covariate disappears. There's nothing really you can do about that, except for people trying to decorrelate the regressives. It's no mathematical trick to get around that problem. You can't orthogonalize one with the other, because that's just cheating. The only thing you can do is go make it more data where the correlation is less, or design an experiment where you decorrelate somehow. It's hard to in your example, but yeah, if you've got correlated regressives, but there is no solution for the GLF. You have to either take new data where the correlation is less. There's no magical system operation you can do to get around that. With structural equation modeling, you could compare different models where, I mean, it's hard to think about, again, your case, but you could say that the global brain damage, which causes the local one, which then causes the cognition, as opposed to there's an effect of the, well, you could draw one where the local lesion predicts cognition, and there's an independent contribution from the global, which those two models will better fit. I think we might get some headway, let's make some progress that way in such equation modeling.
Okay, and so within the world of SEM, it wouldn't be ridiculous to have a line that sort of showed total lesion volume causes local lesion volume, because that causality didn't really happen that way. But
probably the wrong way to
okay, well, that's great.
Depending on, I guess.
Yeah, thank you.
There's a question on Zoom. Please, could you describe what options we have for handling missing data in SEMS? Missing data independent or independent variable?
So SEM is, well, when you have a large number of variables, it's actually a good way to deal with missing data, because you can predict missing data on the terms of the covariance and all the other parameters. So this is the whole field of whether data is missing at random, or whether how much data are missing, but there's lots of tools in structural equation modeling to deal with missing data. There's the full information maximum likelihood is the kind of there's the gold standard way of doing things. If you have missing at random data, it can basically reconstruct values from the covariance and all the other. So imagine you've got lots of measurements of someone, and you've got a missing data point for one of those observations. If you know what the covariance is between all the other subjects, that gives you a strong prediction about what that missing value would be. So the answer is yes. There's lots of ways to deal with missing data within the same framework, although it's a whole field in itself about whether the data are missing at random, or whether there's some, obviously if you're missing a large amount of data and always of a particular type, then it might be hard to reconstruct. But yes, you can do various options to deal with that within SEM.
And there is another question on Zoom. Is there any way how to account for random subject item variance in those SEMs using Lavaan?
Not sure what is meant here, because the residuals are between subject variance, these variables. We're not distinguishing within from between subject variance here, because there is only one source of variance. When we come to longitudinal modeling, yes, you'll be able to separate variability within someone across time from variability between people. But here, I don't think that distinction applies, unless I've misunderstood. I should say I'm not an expert in such equation modeling, so maybe there's something I'm missing here, but I don't think there's any need to distinguish two types of variance here. So it's all between subject variance in this cross-sectional example.
If the person who asked a question wants to clarify, please speak up. But Otherwise,
Sorry, hello.
Hi.
Hello, Rick. Thank you so much for the talk. I have a question regarding the two types of models. One you call the watershed.
Yeah.
So I saw that you can distinguish between the so if we reverse the arrows,
Yep.
like so, like model 3 can be distinguished from model 1 from the simulations. But I
Yes.
was wondering where the information that distinguish these two models come from. If
Yes. Good, very good question. The reason is that if you imagine the covariance between A, B, and C, in the first model here, the covariance between A and B, or between B and C, must be higher than the covariance between A and C. Because these, the way the data are generated, you take A, you add a bit of variability to B, and you add a bit of variability again to get C. So the covariance between A and B, the covariance here must be greater than the covariance between C and A, because you've added another source of random noise. So imagine you go from A, you add some variance to get B, you add some variance again to get C. So the covariance between A and C is less than the covariance between A and B. Do you agree?
so, it's the adding the noise with the stage.
Yeah. Whereas in this case, this model M3 will predict that the data, because the data are generated from M1, the true data will have greater covariance between A and B than between A and C, because these are two links apart rather than one link apart. When you fit model M3, it's predicting greater covariance between A and C than between C and B. And because it's only one path between A and C. And that, so the relative size of the covariances in that 3x3 covariance matrix, the relative size of the covariances differ according to model 3 and model M1. So M1 and M3 and M1 differ in the predicted relative size of the covariance terms, the off-diagonal elements. And when we generate the data with M1, that fits the structure better because M1 fits that better in predicting that the covariance is higher between variables that are one step away than variables that are 2 steps away. So in this model, A and C are 2 steps away. In this model, they're only 1 step away. So the relative size of covariances differ in two models. Does that make sense?
Thanks. Thank you so much. That's clear my question a lot, but I do have a follow-up for that.
Well, just before you follow up, what you might be thinking, and this actually is covered in the markdown, I could reverse it completely. I could put C on the bottom, then B, then A. Why didn't I not reverse it completely? That's a situation where you can't distinguish the order in two models, because after you Z-score the data, if you imagine just swapping A and C, the relative patterns of covariances would be identical. So it can't, structural modeling cannot infer all types of possible directions. There are some limitations to what you can do. And it can't distinguish A, B, C from C, B, A. And that's in the code. If you want to try this, it's commented out, but you can actually get the same model fit, numerically identical model fits, when you generate data from M1 and fit with a fully reversed M3 as which you fit this true model. That's yeah. So this bit here, sorry. So I did explain this here. We could fully reverse it to have B. That might be a typo. Anyway, if you use this code here, where you assume that this is a reversal of the true data, so A caused by B and B caused by C is different from B caused by A and C caused by B. If you do that, run that code there, you'll get identical fits after Z scoring. So there are limitations of what you can infer. Funny enough, you can distinguish this model from this model, but you can't distinguish a fully reversed case because the relative covariances are identical in those two cases. Now, is that going with your follow-up question?
So I do one, or maybe I should play with the R code to find out this follow-up.
Yeah.
But I was wondering what would happen if there is still a path between A and C in addition to the one joining M1. What if there's still a path between A and C? and will that make the arrows more difficult to distinguish? Like,
if you added a direct path between A and C, but the data did not use that path, then it should still favor the parsimonious true model, even when you reverse it. But if you generate data where there is a direct path as well, then it won't be able to distinguish. So if you had a direct path in A and C, and you compared this model with one where you swapped A and B and had direct path as well, then I think you wouldn't be able to distinguish it anymore.
so it's
Because those three paths could explain any relative pattern of covariance. So in the 3x3 matrix, there's 3 off-diagonal elements. With 3 paths, you can explain any relative size of those covariance matrices. So you wouldn't be able to distinguish them.
I see. Thanks. Thank you so much.
Yeah, sorry, it's confusing.
Thank you. I just have a more practical question about kind of the size of the data frame or the number of observations you had, because at the beginning you talked about needing a large volume of data.
Yeah.
I'm interested in looking at predictive relationships, but working in rare genetic diseases, you have much smaller sample size. So is it the case that you'd stay away from this kind of modeling, or are there alternative approaches, or are there kind of caveats that you need to build in constructing your models?
Yeah, that's an important question. Subsequential modeling, to get it working, you need to be able to estimate a covariance matrix. An estimating covariance matrix requires a large number of data points to actually estimate it. The general rule of thumb is you need at least 10 times as many observations as you have variables in your model. So you don't need 10,000 as I had here. That's just to get you precise estimate. But if you were dealing with 3 variables, you need at least 30 observations. There's another suggestion actually that it's not the number of variables, but number of unique covariance elements, which I think is more accurate. So if you were dealing with 4 variables, in terms of the covariance matrix, you'd be estimating 3 plus 2 plus 1, 6 different covariance terms. And I'd say you need at least 10 observations per covariance term. So that's 60. So if you're dealing with 4 variables, you need at least 60 participants. Obviously, the more the better. Obviously, you can run it with fewer, and you can do various tests of the assumptions behind the model. But generally, for these path models, you do tend to need quite a lot of participants. Yes, they're designed for large-scale data analysis. But yeah, it's not possible to do it with a small n if you only have a small model. If you only have a few variables, you don't need many participants to estimate the covariance.
Thank you.
Yeah, earlier you mentioned that you thought that structural equation modeling was better than a PCA, and I am naive to SEM as of an hour ago. And so could you just explain a little bit more? It seems like they have different use case scenarios, and that PCA is more data driven, whereas this is more, you have kind of a priori assumption about the underlying interactions in your data. So can you explain why you would say one is better and how they could be employed in the same setting?
So let's just say you have 3 variables. If you do a PCA, you are basically assuming that each variable is measured equally precisely, has the same true variability and the same noise. So also, it's very important to do PCA to take out the scale of the variables. Say you did a PCA with reaction times in milliseconds and accuracy in 0 to 1. If you do a PCA on the raw data, the first component will be dominated by the reaction time variable. That's scaled more. So you nearly always Z-score your variables for doing PCA to make sure they're the same range. But even if you Z-score them, they have the same range. The first component will be the linear combination explains the majority of variance in the data, assuming that each of them are equally important, which is fine in many cases. With the factor analysis approach, which is basically the measurement model of SEM, you are finding a linear combination of them, but the paths that relate the contribution of each of the variables to the underlying latent structure can differ, not only in terms of the variance explained, but in the estimate of the residuals. So it can account for that some variables may be noise in others. And the very similar concepts, you're reducing 3 numbers to 1, but slightly different assumptions. As PCA is fine if you've got no a priori reason why no knowledge about why these parameters, some of these variables may be more noisy than others, then PCA is fine. But generally, I recommend the extra effort of doing factor analysis in SEM is generally recommended if you want to extract a latent variable. You can have more than one latent variable, so you don't have to just take the first component. You could take 2 latent factors. You need to have the only limitation is that you can do a PCA on 3 variables and get out 3 latent factors, which are different linear combinations of the data. And the first one might explain 2% variance, next one 30%, and the last one 20%. With factor analysis, you can only estimate a small number of factors and you have variables because you're estimating not just the pars but the residuals as well. So that the situation where PCA is, if you want to identify more than one component, PCA can identify as many components as there are variables. This approach in structural modeling, you're limited to estimating fewer latent factors than you have measurements. But yeah, if you're only care about the first dominant measure, then I would recommend doing it all within structural modeling. Yeah.
Okay, the final question.
Another follow-up question about mediation, which is really interesting. So the way I expected you to set it up was the other way around. I thought you were going to say, how does what happens in the brain mediate the effect of age on cognition?
Well, that is this.
Oh, that's how. Oh, so M5.
Yeah, that's moderation.
Oh, sorry, moderation. That's what I mean. Yeah.
Term,
Yeah. So moderation.
Yeah.
So that the way that's set up is to say, how does age moderate the effect, the relationship between the brain and cognition?
Yeah.
So if you wanted to ask the other question, which was how does what's happened to the brain moderate the effect of age on cognition, you just swap A and B. Is that equivalent, or is that actually a different model?
It's equivalent.
Okay, super.
The interaction is symmetrical. Yes, you can't tell what the saying that A affects and what affects. So say that age moderates the effect of brain cognition, same thing, brain moderates the effect of age. Yeah.
Okay, thank you, Rick. That's very helpful. What's the point? No, we can stop recording.